So where did Hutton come up with these ideas? He visited several localities. In this map, this Google Earth image, you can see 4 red circles, and the upper red circle is in Glen Tilt in the Grampian Highlands of Scotland. Edinburgh is the second circle, just below that and off to the right slightly. Even farther to the right on the edge of the North Sea, that's Sicker Point. And then lastly, Jedboro is the circle that's in the southern part in the highland, the lowlands of Scotland. And so if we go to each one of these locations, there's an OS Ordnance Survey map of the River Tilt. And Glen Tilt is the name of this area. And you can see it on the map up there, the inset map. If you go to Google Earth, you can actually do a tilt and a pan of this area, but there's a photograph of the area that he was looking at. What Hutton found in Glen Tilt is like no other place in the Grampian Highlands anyway, where there's a granitic intrusive into rocks they're really metamorphic rocks, but he didn't know that at the time. In fact, nobody had ever heard of or nobody understood metamorphic rocks back at his time. So this would have been in the 1780s, late 1770s. So this granite actually cuts schistose rocks right at this waterfall. Resistant rocks show up oftentimes at waterfalls. He made a map of this, in fact, and so he mapped the intrusion of the granite, shown in the pink here, cutting through these layers of schist. And so everything is kind of crystalline here, but in fact, the metamorphic rock he illustrates here in a sort of the light and dark colors, and then of course the pink is the area that is the intrusion. And so the granite was just kind of like shot through all of these metamorphic rocks. And it shows, first of all, cross-cutting relationships. Steno had already talked about cross-cutting relationships, so he knew that the granite had to be younger then. And maybe that is his evidence then for these being, a result of Plutonism. And of course, he's right. In this case, the Pluton was the granite intruding into these metamorphic rocks. And so that's the first line of evidence. And so that's what helps support his ideas that, Plutonism is the way to consider, the origin of most rocks on this planet. The next location is in Edinburgh, and it's a special area. It's called Holyrood Park, or Holyrood Park is how they pronounce it in Scotland. And you can see here an area that's circled called Arthur's Seat. But then also, if you head off to the west from there, there's the Salisbury Crags. And they show the little asterisk sort of symbol on the map, the blue asterisk. That's a viewpoint, if you will. So there are trails all over this park. And in fact, it belonged to the King of Scotland. And so this was the area where he would go riding and hiking and walking, so forth. But it's, the people's land now. And you're right next to the city of Edinburgh. So Holyrood Palace is off to the north there. And then you have the Royal Mile, which stretches off to the southwest then from that and goes up to Edinburgh Castle. So the Scottish Parliaments, that you can see this right there. They value science, so there's the Discovery Centre there, and there's the Scottish Parliament there. So let me show you some photos from there. Okay, well, here's the Google Earth image, and that's Arthur's Seat. That's that area in Holyrood Park that we were just looking at. And Salisbury Crags cast the shadow that's a little bit closer to the Royal Mile over here. And so we're going to zoom in on these areas. And so the first photograph in here, you can actually see Salisbury Crags cropping out. When I went here, this was pretty close, maybe within a mile of where I stayed at Airbnb. Arthur's Seat is the high spot in the park. It's the little hill there, the little peak, if you will, a small mountain, I suppose. And then you can see a view from the Edinburgh side then. So if we were on the south side before, the second image, the one on the lower left-hand side, is looking from a little bit farther to the north, looking to the south. You can see Arthur's Seat along the horizon there, and you're actually closer to the Salisbury Crags here. And then lastly, if you get real tight and up close to about where the arrow points in the upper panoramic image, real near there's the Salisbury Crags crop out, and then looking over the top, if you were to look over the cliffs there's Arthur's Seat again. So I have to introduce you to some new terms here. Dolerite. Now, dolerite sounds like the rock dolomite that you may have seen when you're in Geology 110. Dolerite is actually not a term that we use in the United States. It's a British term, but it means diabase. Well, the American version of the same word is diabase. And diabase is a very fine-grained igneous rock that's intrusive, but it looks like basalt. But it's so fine-grained, you can call it a microgabbro, is another sort of term that people use for it. But diabase and dolerite are interchangeable, really, but the British version is called a dolerite. And that's what the Salisbury Crags is. It's a dolerite. It's an intrusion. In fact, it's an intrusion that came into flat-lying sedimentary rocks, and we know that today as a type of pluton called a sill. And so that sill crops out across the horizon when you look at it from Edinburgh. Arthur's Seat, on the other hand, happens to be a volcanic edifice, or it's the tip of a volcano, essentially. The top of the volcano has been eroded away, but it is the neck of the volcano in that vicinity. So this is such a famous place. Now, Hutton spent a lot of time in Edinburgh, and so he was all over Holyrood Park all the time, and he would take his friends over there and say, hey, check us out, And so what he saw there was a sandstone that was in contact with this intrusion, this dolerite intrusion. And so they call it Hutton section here. You can kind of see the image, the sketch, if you will, at the very bottom there, and Hutton at the top, and shows you the location here in the park and so forth. But that's at the Salisbury Crags there. Now, with this slide, this is my own version. I'm trying to repeat. What did Hutton actually see there? And then you can see in the next image here, this is Nancy standing up next to the dolerite. She's got her hand on the dolerite, but that's the sandstone bed right there that's been cut by that dolerite. Notice that the layers in it are even cut, so it's a blocky it's not a loose block, but it's been kind of folded, if you will, and then the intrusion kind of wraps around it essentially. And you see the same thing actually in the upper photo that shows the upper contact of that dolerite with the sandstone bed. And so, in fact, using the idea, the principle of cross-cutting relations, this is an intrusion. It's one in which the younger rocks cut the older rocks, obviously, right? So what's older? The sandstone. And the dolerite is younger then. So if we look at the Arthur's Seat area then, that's the agglomerate or volcanic breccia at the very top of that hill. And in fact, you can also find the diabase, the microgabbro, also at the top of that hill as well, but you find columnar joining there. Well, okay, I don't know if you had this in Geology 110 or not, but columnar joining is the same style or the same sort of process that led to the formation of Devil's Tower in northeastern Wyoming. Maybe you've seen images of Devil's Tower. You can see the kind of hexagons or the pentagons and all that sort of polygonal shape. That's all a result of cooling. In this case, it is an igneous rock that cooled very close to the surface, and so columnar joining is one of these processes that you commonly see in basalt flows, say in the Pacific Northwest. You see it in Devil's Tower. You see it here also. And so that's at not so much Salisbury Crags, but very close to Salisbury Crags here. So Arthur's Seat itself is kind of like the vent area for that. And so you can see the volcanic breccia around this. And so when the thing blew up, of course, it's like a composite cone kind of volcano. Even it's mostly mafic composition in this vicinity, but you can actually see the broken pieces of rock that were incorporated into that volcanic breccia. And then for the other three images across the bottom, they're all columnar joining. And so you can see large columnar joining at the bottom. That's St. Anthony's Chapel next to it there, the ruins of St. Anthony's Chapel. And the first image in the bottom row there, that's Nancy standing on some columnar joining, and then Arthur's Seat is actually up in the distance there. But if you're actually right on Arthur's Seat and looking down, you can see the columnar joining there from the cooling of that magma once it had intruded into that volcano, if you will, into the volcanic neck there. So those are two of the locations, Glen Tilt, and then Edinburgh at Holyrood Park. You can see in Arthur's Seat and also the Salisbury Crags there. The next place he went to was one in which he was just exploring, essentially, along with his friends, actually. He took along with him John Playfair and also a fellow, Sir James Hall, who was a friend and part of the Royal Society, essentially the Fellows of the Royal Society of Edinburgh. And so they have their own version of the Royal Society in Edinburgh. So if you ever see FRS, it's Fellow of the Royal Society. FRSE stands for Fellow of the Royal Society of Edinburgh. And so it's a title that people have. If they're members, they have to be chosen to be a part of that. So Sicker Point is the place that he set out to find. He didn't know where it was. He wasn't looking specifically for Sicker Point, but he was looking for a contact. And so they sailed south along with the ship's crew in a sailboat, obviously. And they kept sailing, and they would go by these massive conglomerates that were part of the old red sandstone, Devonian in age. And it's like, wow, look at all the pieces of rock in here, derived partially from the rocks immediately below, which would be the Gala group of which is Silurian in age. And so as they sailed along, eventually they got to a place where they could see that there was an unconformity. And it's like, oh, those rocks cut those rocks. And they beached the boat and they came ashore and they spent the entire day here looking at that surface that shows where there are vertical rocks that are overlain and cut by erosion at that surface, then overlain by Devonian age rocks. So the Silurian in the right-hand side here, that's Nancy sitting on the Silurian there. And you can actually see the Devonian roughly about at the head of that arrow there. And so some of the vertical beds tend to stick up a little higher than the ones around it. So it's a little tiny conglomerate that traces across that surface there. It's called the Sicker Point conglomerate. And in fact, so they land with the sailboat here. They get out. They essentially have a picnic. There's a little cove right next to this. Was a Smuggler's Cave right next to the Sicker Point location here. But for Nancy and I, we actually hiked down a pretty steep trail. It has a little rope that you can hang on to, and pretty much little foot pads that you could place your heels into as you're heading down what is essentially about a 60-degree slope. So luckily you don't have to wind up at a heap at the bottom. They have a place where you can grab onto when you make your way down there. There is a pasture at the very top up there, and I think there were 3 bulls in the pasture and a whole bunch of cows, and they almost stampeded on us. But we stayed close to the edge there, as close as we could get to, and I sang my cowboy songs to get along, little dog, all that sort of thing, to calm down the cattle. But they didn't trample us, and the bulls didn't care. And the bulls just kind of wandered off in a different location, and the cows eventually wandered off into another part of that field. If you look at Sicker Point up close, you can see this sort of relationship. And so it's the same one that Nancy was in, but a little bit brighter day there. Absolutely gorgeous. So the next one is a panorama, and you can actually see the Smuggler K there. And you can see the same stratigraphic relationship across and above the cave there. You can see the reddish beds of the old red sandstone overlying vertical beds, and you only see the bases of the beds or the tops of the beds. I don't know which they are, probably the base of the bed in vertical context there below that sandstone. It's an absolutely amazing place. I have some videos I'm going to incorporate into this if I have some time to do this, so I'll try to draw those into this as well, and maybe splice it in somehow here. But anyway, Sicker Point is, if there is any sort of sacred place in geology, this is it. When they were here, Hutton thought about this, and it's like, okay, how do you take beds that are originally horizontal and you put them upright, right? And if you put them upright, then you have to raise everything up, right? And in this case, and then you had to erode everything, and then you had to plunge it back under the sea, and then you had to deposit these sandstones and the conglomerate and everything above that is like, my gosh, that must have taken millennia, thousands of years, hundreds of thousands of years, and maybe even millions. And in fact, that surface they've estimated is roughly about 55 million years of time missing there, which is absolutely astonishing from a geologic standpoint. So in other words, Hutton's epiphany at this locality was that it's like, oh my gosh, the Earth must be absolutely ancient. And that's where he came up with this idea that there was no vestige of no vestige of a beginning, no prospect of an end. And he thought that the Earth was essentially eternal, didn't have a start, didn't have an end, but we're just out here in space, flying around the sun. Okay, so the next slide gives you a little bit more detail on how it formed, and we take these horizontal beds that are deposited 400 million years ago, Silurian age. We fold them, okay? That's what mountains do. They tend to fold rocks and tilt them and so forth. And then you erode that layer, right? You have to uplift it, and then you erode it. And then you have to plunge it back under the sea, and then you have to deposit the old red sandstone over the top of that. And then after that even, you'll notice that the old red sandstone was slightly tilted too, right? Well, there was another tectonic orogenic event that slightly tilted it after that. So it's compacted even after its deposition as well. So 5 stages to that development of an unconformity here, the most famous unconformity in the entire world. And for geologists, a sacred point, a sacred place. I'll tell you what I really liked about visiting this locality. Wasn't expecting anything other than kind of a touristy sort of thing. And there was nobody there. It's on a farm. You park in a small gravel lot. We were the only people there that day. And there wasn't a bit of trash. There wasn't a bit of litter anywhere along this place. And you can see the reverence with which they take care of it, so it's very well looked after. Okay, if we go on finally to the last of Hutton's famous localities, this is Jedboro in the lowlands of Scotland, and you can see the unconformity here in his illustration at the top there. And the actual unconformity is nowhere nearly as well exposed as what it is at Sicker Point, but you can see a close-up of it on the right-hand side and more distant shot on the left-hand side there. But this demonstrates there has been uplift erosion and then deposition over the top again. So there's missing time there. There's missing time and evidence for an orogenic event of some sort. And that completes the part of who is probably the most important geologist who's existed, in helping us understand the age of the Earth and so forth. So we know today that the Earth did have a beginning. We know that it will have an end in roughly, we're about halftime right now. So, it's like ideas have changed through time, but those ideas that he had, they're still with us today. Now, we know today that there are metamorphic rocks, but that information didn't come out until the late 1800s, early 1900s. We know more about the structural geology, much more than what ever could have been known in the early 1800s. And so, and Scotland is a place for studying these sort of rocks and those sort of relations. So the first thrust fault ever described was from the Highlands, the Northwest Highlands in Scotland. There are places like the Great Glen Fault. There are also the Highland Boundary Fault. Highland Boundary Fault has metamorphic rocks right next to it, and you can actually map out the metamorphic grade away from the Highland Boundary Fault. So Scotland, a great place for geology, great place to learn about geology. So that's the story of Hutton. Okay, well, that's part of the story of Hutton. Hutton actually trained to be a doctor and then in the law, and then he eventually thought he would become a farmer then. And of course, he was a gentleman. He didn't have any title or anything like that, but he was awarded a title, I think, later on in his life. But in 1785, he published on these sort of findings and talked about the antiquity of Earth. And Playfair made it, easy for him to become more popular, I guess, after that. So If you're interested in it, there is a book about this, and it's called The Man Who Found Time, and it's all about Hutton, and what it really talks about is the discovery of deep time in Earth history. Before that, everybody thought you had to reconcile this with the 6,000-year, record of Archbishop Usher, and he didn't feel constrained to do that. And it's not that he was an atheist or anything like that, but he just didn't feel the need to call upon supernatural circumstances in order to explain the earth. And that's one of the actualism is all about that, So it's like, what do we find and how do we explain it? Other books to talk about for Steno, when we talked about Steno, it's The Seashell on the Mountaintop, I think is the name of the book. I just finished that this summer and read about Steno's discoveries and his relationship to the Medicis and so forth. For this guy, this is the next person on the list here about how the development of science really, and geology in particular, came about. His name is William Smith, and sometimes people call him William Strata Smith because he looked at strata a lot. And so there is a book about him as well. That's called The Map That Changed the World. And he made the first geologic map of any consequence. And so he mapped southern Scotland. He mapped also Wales and England. And he showed where different rock types crop out. Now, he was this fellow, you already have heard parts of this, but he was a jobbing ditcher. And being a jobbing ditcher, he would drain the wetlands or the fens that cut across the eastern part of England and drain the water out of them. So people hired him. And so when he did that, he found fossils. He got down to bedrock. He compiled all this information together, and he made a map. And so in that map, which is on the next slide here, he published that in 1815. Now, 1815 was a momentous year in the history of Earth. 1815 is the year that Mount Tambora blew up in Indonesia, and people didn't realize it was the next year then became the year without a summer because of all of the volcanic debris that was up in the atmosphere. It reduced the amount of energy in atmospheric energy, and so places like New York Harbor froze over in the wintertime. There were crop failures and things like that, and of course Mount Tambora itself killing 92,000 people. So it was a bad time, right? And so, but that's the year that he published this geologic map of Britain, of southern Britain anyway. And so you see, he did all of this work. He didn't have anybody to help him publish it. There was one underwriter on this who was a friend of his, and he was just about broke, actually. And this is a guy that had he was on the road all the time. He had marital problems. He had all sorts of things going on, and he did not have a lot of money. And in contrast to every single other scientist that you've heard about so far, they were either gentlemen or members of the clergy. He was trying to make a living at the same time. And so he was not a gentleman. He was born into the middle class, if there was such a thing back in the early 1800s here, 1700s when he was born. He eventually got the map published, and of course he gave a copy to the Royal Society in London, and they began to plagiarize it. They just actually took his information, published it verbatim, but eventually he was justified, and so people came along and, oh, this was your work. Oh, okay, that's good. Well, see, he didn't fit in with the folks of the Royal Society because he wasn't a gentleman. But at the same time, they eventually awarded him a prize called the Wollaston Prize. And if you're taking mineralogy right now, if you've taken it in the past, you'll know that wollastonite is one of the minerals that you'll have to memorize at some point. So the Wollaston medal belonged to him, and eventually he died just within a year or two, I think, after having been awarded that medal. But he made a huge contribution by making the first geologic map of Britain. In fact, it's not the first geologic map, because you've already seen one that Hutton did, a small-scale map. There was actually one in the United States, too, by a guy named McClure. And McClure did one of the entire eastern seaboard and up into the Appalachians But at the same time, he only had like maybe 6 mappable rock units on it. And so he would say things like, these are the mountains, this is the coastal plain. And so, in other words, this was the most detailed map up in that point. And so you could tell on his map where the coal measures were. That's the black areas on here, or the areas that are just above the coal measures in the gray. And so he made this incredible discovery. And not only is if you stripped off all of the vegetation, if you strip off the soil, there's bedrock there. And so he knew that, and he put that into practice. And it's like, then you can predict where you're going to find these rocks. And if you can predict things about where resources occur and things like that, you're way ahead of the game. And so that's what most geologists do. We wind up mapping things. And so, William Smith was like one of those sort of like heroes to geologists everywhere. And so that's the map that made him famous there. So on to the next slide, we have Georges Leopold Cuvier. He was the founder of the catastrophist school of thought. So far in this, you heard about Plutonism, you've heard about Neptunism, and now you're hearing about catastrophism. So Neptunism was about the world was water-made, or rocks were water-made. Plutonism about fire-made. And catastrophism actually called upon pretty much catastrophe after catastrophe. So really, it puts it more back into a supernatural sort of like frame of reference. Cuvier himself was the director of religions of the Protestant religions in France. This is the Age of Enlightenment, right? But he was placed in charge to try to keep the religions within bounds. Okay, so France had a long history with different kinds of religious beliefs, Huguenots, and then also the Cathars, and there were a whole series of Protestant religions, or let's say almost cult-like religions, like with the Cathars, although they were very kind people. But all of these offshoots resulted from dissatisfaction with the church structure itself. But France, in this enlightened age, actually had a separation, and they cooperated with one another, both the Catholic and the Protestant religions. So Cuvier was in charge of that. His idea of catastrophism, however, incorporated a lot of biblical Christian thought into it. And so he thought that there was one creation, then it was obliterated and destroyed, and another creation, then it was destroyed. And so the series that we're in, when he was in this, he thought, well, there was a universal flood. That was another one of these catastrophes. So it stands in opposition. The catastrophism school stands in opposition to what uniformitarianism promoted, which was that there was slow evolutionary change, in the earth. And this is pre-biological evolution, but just slow changes in the earth. And the things that we see today are the same processes by which the ancient past had operated as well. Today, we know that there's actually both going on. Some catastrophes do occur, like meteorite impacts, or there's mega floods and things like that can occur. Not biblical floods or anything like that, but for instance, mass breakouts of like ice damming and things like that can occur. So catastrophes do happen and are recorded in the geologic history, or the geologic record, but they're very uncommon, I guess I would say. So most of the time, uniformitarianism seems to be how the earth works. So that's the story behind Cuvier for the most part. I will mention that Cuvier had a daughter who was an equally brilliant young budding geologist, but she passed away when she was 28, Sophie. And life went on for him. He became tireless after that and worked incessantly doing his geologic studies, and so he was a brilliant man in and of its own right. his own right. By the way, we are going to get to the women of geology here very shortly. The trouble is that back during this time, that was a male-dominated culture which existed in Victorian Britain and earlier. So we'll go on from here, and that would be the next person that we're going to talk about is Charles Lyell. Charles Lyell is another Scot. It's getting one after another, isn't it? It's like one, Scot, and then there's another Scot. Well, okay, Smith was English. There's a few other folks that, Italians and Danish and German and so forth. But you can see where a lot of the thought at this time was in Scotland. Lyell published the first geologic textbook. It's the one that Darwin took with him on the journey around the world, right? That they did on the HMS Beagle. And so he was also one of Darwin's mentors. And so in that, he learned directly from the master, the guy who wrote the textbook. And so he demonstrated cross-cutting relationships after Steno had already mentioned them, but he made them much more specific, I guess. Let me put it that way. And when it's in a textbook, it's just easy to spell it out that way and illustrate it for that matter. So this was an illustrated book, of course. And he also came up with a new one, actually, a new concept, and that was the principle of inclusions. If you find inclusions in a rock, that means that those inclusions have to be older than the rock that they're encapsulated in or incorporated into. So if a cluster grains from one are incorporated in another rock, those clasts tend to be older, or they will be older. So that's Lyell. You see here, we're gonna deal with Lyell again when we talk about the history of the geologic timescale. But know that he was famous for being one of Darwin's mentors, and then also from this idea of inclusions. So inclusions are a little like cross-cutting relationships in the fact that the older rocks are now incorporated into the younger rocks. So for our next person is a famous geologist. You may know him more as a biologist, but in fact, he started his career as a geologist, and that's Charles Darwin. And he studied also with a geologist named Adam Sedgwick. We're going to look at Sedgwick some more when we talk about the geologic timescale as well. It was Sedgwick who proposed the Cambrian time period, and Sedgwick and Darwin who took a trip to North Wales to look at the Cambrian rocks of North Wales. So, these are names that are probably, certainly Darwin is very familiar with you, but these are the shoulders that he stood upon when he learned his geology. And so Sedgwick is a very famous geologist. And it was Darwin who proposed this idea of evolution by natural selection. And today we know there's like 4 major processes that are going on in evolution, but certainly natural selection could be one of those. And so he also collected fossils on his voyage around the world on the HMS Beagle as the ship's naturalist. And he wrote The Origin of Species based on his discoveries during that voyage. Most of his famous work was actually related to the evolution of the finches on the Galapagos Islands, but he also had some other very important contributions that he made. For instance, he was able to propose this idea of coral atolls, that reefs would grow around volcanic islands, and that the island itself may subside below the waves at some point. So he came up with that idea. And then also he discovered all sorts of bones and fossils and so forth that went into the collections of the British Museum. And so those are still there today, even today. So that's Darwin. Our next hero of geology is Louis Agassiz. Agassiz was Swiss, and he immigrated eventually to the Americas to actually, I think he was at Harvard. And so Louis Agassiz studied glaciers in the Alps. And it's Swiss, right? And so it's the natural thing to study there. And when he studied these, he saw all these glacial features in the sediments around the mouths of glaciers, for instance, moraines and all sorts of other textures of related to glaciation, alpine glaciation. And so when he went into Germany and places around Switzerland, he began to see glacial features there. He says, wow, the glaciers once extended all the way to this area. And of course, the people who heard that the first time said, oh, you're full of it, and so in their own language, of course. But he proposed this ice age hypothesis that within, the Pleistocene, there was an ice age. He didn't know about the Pleistocene and hadn't even been named yet. Lyell would do that later. But the ice age hypothesis was made. And when he came to America, he began to see the same sorts of things in New England. So, for instance, even Manhattan has glacial deposits on it. Okay, so he saw this and said, "Wow, this seems to be an important feature." And so that's the contribution that Louis Agassiz made, was this idea of an ice age hypothesis. Our next person is, okay, we're going to start tapering off maybe a little bit here, but James Hall was pretty important also in America. Now, this is a different James Hall from the Sir James Hall, who was the fourth baronet of Dunglas in Scotland. This James Hall, I think it was at Rensselaer Institute, but he became a famous geologist, and he was a state paleontologist, in fact, for the state of New York. And he pioneered studies in New York as well as in the Appalachian Mountains. And that was when it was pioneering work for geologists to do this sort of work. And he recognized for the first time this idea of subsidence, which is the ground sinking, and then also uplift associated with the mountains in the Appalachians, for instance. Our next hero of geology, who gave us not so much ideas and concepts, but he certainly gave geologists this sort of romantic, exploratory sort of vision for how we should go examine the earth. That is John Wesley Powell. I can't say enough about John Wesley Powell. He actually served in the military in Missouri. He was a federal officer at Fort D in Cape Girardeau and helped design that fort. I don't know if you're familiar with Cape Girardeau on the Mississippi River in the eastern side of the state. Fort D still exists, and so that was one of his engineering sort of marvels, I guess. After he was at Fort D, and I think he took part in the Island Number 10, the Battle of Island Number 10, I think it was. He went on to Shiloh, which was early on in the war in Shiloh, Mississippi. And of course, he lost his arm to a saber there. They cut his arm off, but it didn't stop him. Here's a guy who still went on to do great geologic wonders. And in fact, he led the first boat expedition down the Colorado River with his brother and a host of other men who plied the waters of the Colorado for the first time, not knowing where they would wind up, going through rapids and eventually making it out of the Colorado River. 3 of his members died on that trip, but they were the ones who left with copies of some of the materials as they were making their way down the river. They didn't know if they would be able to get out through the river or not. And so the 3 that left and went north and were never heard of again. So, but after his great discovery in 1869, going down the Grand Canyon, the Colorado River, he eventually became the second director of the U.S. Geological Survey. And the U.S. Geological Survey is the premier research institution of the federal government of the United States. So the USGS has a worldwide reputation for doing quality work. I work for him. Okay, so did my dad, actually. So he was famous, and so now we're going to switch hats a little bit. And there's a new movie out. I don't know, this whole situation about COVID-19 has everybody, so you can't go to movie theaters and things like that anymore. But there is a movie, as I understand it, about Mary Anning, and that's her little dog down here next to her in this painting. Notice she has a rock hammer. Again, that symbol of geology, right? So if it's not a single pick, it's crossed picks. So Mary Anning was a fossil collector and a dealer, and I think her father passed away early, but she was also a paleontologist, and so she would excavate fossils along the seashore close to Lyme Regis, I think it was, is where she lived. And so the Blue Lias cliffs, Blue Lias, Lias cliffs, were exposed there. And there's this enormous amount of fossil material in that area. And so she collected those fossils. And many of the fossils that she collected actually wound up in North America because I think it was the Natural History Museum in Philadelphia bought her collection, some of her collections. Ethelred Bennett is another famous woman geologist. She was a fossil collector as well. And, it's her collection. Sorry, I should read my own notes here. But she's the one who sold to the Academy of Natural Sciences in Philadelphia. Both of them, though, collected these fossils. And so if you ever hear the phrase, she sells seashells by the seashore, that tongue twister, that's Mary Anning. And so they made a movie about her just recently here. Now, sadly, her little dog was killed. The dog was in her knapsack, her basket, and she was working on an excavation trying to get the fossils out when a rock became dislodged from the cliffs there and killed the poor little dog. But still, she's an amazing sort of geologist, an amazing person. So, the initials AWG at the bottom of this diagram, that stands for the Association of Women Geologists. It's a great organization. You know, at some point in your career, you're going to, first of all, join the Geological Society of America. And that's cheap for a student to do that. I think it's $20 or $25 to join that. Make sure that you do that. If you do that, you're going to get connected with a society that cares about geology, that cares about learning geology. And then AWG is a subsidiary or society affiliate for GSA. And so AWG has awards and breakfasts. They have scholarships. They have all sorts of things that can help you as a student. And you don't have to be a female in order to actually join AWG. Now, my wife is a member of it. I have not joined it because I didn't think that she needed me to tag along with her on the breakfast that they have every time that the convention is held. But it's a great organization, so AWG. Our next famous woman geologist is Florence Bascom. She had a master's in Wisconsin, and then a PhD from Johns Hopkins, and then she went on to teach at Ohio State, and then Bryn Mawr, and she had a position, in fact, with the USGS. Now, she mapped a lot of the Appalachian Mountains and part of the Piedmont region, and that's one of her maps, actually, off here to the side. But Florence Bascom, famous, the first woman ever employed as a scientist for the U.S. Geological Survey. Very important sort of groundbreaking sort of like a person who came in to make her mark in this world. Our next famous women, and I've kind of cut to the chase on this, but there's a few of them. Inga Lehmann is the first here. She's the one in the middle in these photographs. Inga Lehmann discovered that the inner core was actually solid. And, you know, that's pretty profound. She's Danish. Isabel Clifton Clarkson, Australian, paleobotany, taught at the University of Melbourne. Marie Tharp, who you see down here on the left, she was a co-discoverer of the mid-ocean ridges. I think it was Matthew Maury who was also with her in those discoveries. Tanya Atwater, she's still alive. Okay, she's the only one so far that we've talked about that's still alive. She was born in 1942. She used to work for the USGS. She's at University of California, Santa Barbara now. And she did incredible animations when computer animations were just beginning, and she would show the tectonic evolution of California. And so she made some groundbreaking sort of like graphic contributions to the science of geology. And there's a whole bunch of other notable female geologists. There are notable black geologists. There are notable Asian geologists. It goes around the world, and it goes and cuts across every ethnicity and race, if you will. So the next slide is to promote to you the AWG. That's the Association of Women Geoscientists. And then also the NABG, which is the National Association of Black Geoscientists. And then also there's an organization for gay, lesbian, transgender, and queer folk from it's NOGLSTP. And so I don't know how they pronounce the whole string of letters, but it's nice to know that there are groups out there that support you either for your gender, your race, your ethnicity, or your identity, or your passion, I guess you could say. So this is the end of this part of the history of geology. I will make a comment, and I will say that geologists are the most accepting, wonderful, diverse sort of group of people, except we want more diversity, and yet it's very difficult for us to get diverse students to become interested in geology. We very commonly get students who are interested in camping and the outdoors, and too often it's not the interest that many folks have that are of color, and it's like, and so we'd like to change that. We want to make sure that we get folks interested in geology who are from these diverse backgrounds that can add to this wonderful group of people you're going to meet and then get to know for the rest of your life, essentially. So they're a great bunch of people, and it's wonderful. I have friends, African friends. I have all these different ethnicities. One friend's Muslim, and I have all these different friends that I've made over the years, either in grad school or on as I met other folks, I guess you could say. To build and break down the barriers, it's really important, and to make everybody feel comfortable, because this is the most easygoing bunch of people I've ever met in my life. And most of them are pretty good. I say most of them. I can't say that all of them are, sadly. I wish I could. Anyway, that's it for now, and I will get on with the history of the timescale next. So thanks for your attention. This is part 2 of the history of geology.